Good morning, everybody, and welcome to this PhD seminar, Aerospace PhD seminar. Today we have with us Alberto Racionero. Alberto did his master and his bachelor at the University Politécnica of Madrid in the aerospace engineering. Then he moved to Torino to do a PhD in the MUL2 group. That is a group that essentially specializes in multi-layer and multi-physics analysis of structures. Okay, and then since April this year, he's a doctor and he's working as a postdoc in the same group. Okay, and today he's going to be talking about advanced multiscale modeling, uncertainty quantification, and optimization of variable stiffness composites through a unified structural theories. Okay, so Alberto, the floor is yours.
Okay, thank you everybody. Thank you for coming today to this talk. So yeah, I wanted to start by just acknowledging other people that also contributed to this work. So not only me, also it's the work of my advisors from Politecnico, so Professors Alfonso Pagani and Marco Petrolo, and also some other colleagues from MUL2 and from other universities like Virginia Tech or some colleagues in the University of Washington, also some research colleagues in Embraer. The menu for today is as follows. First, I will briefly talk about the state-of-the-art of automated fabrication processes in composites. Then I will move on to introducing the variable angle toe composites, where are their advantages. Subsequently, I will move on to the structural modeling part. So we're gonna learn how to model from the macro scale to the micro scale of these of composite materials in general. Afterwards, I will show you some results and techniques that we can employ to model defects. And the last part about regarding numerical results is focused on the structural optimization of variable stiffness and what are the possibilities that these kind of composites offer compared to straight fiber composites. So regarding the state of the art, as we know, I'm not going to start today with the classical slide where we show the parts in the aircraft, which are made of composite materials. We know that in the beginning of incorporating, when composites were incorporated in aircraft, they were manufactured, these components, by hand layup, basically by very well-trained operators. However, with the irruption of and the innovation of new manufacturing technologies, we are able to create large volume structures with these automated strategies. These machines are basically the automated fiber placement, AFP, and the automated tape laying, ATL. And as I said, they allow to cover very large volume structures, deposit, lay down with a high deposition rate, and also maintain the good quality, the high quality required to this kind of applications. As I said, with these new manufacturing strategies, we can manufacture composite structures. From what we have learned at university, we learn normally about straight fiber composites, in which the fibers are oriented in a constant direction within the layer, and then by playing with the number of layers or the orientation of these fibers, we can tailor the mechanical response of the structure. But now with these new capabilities of AFP, we can conceive a new family of composite structures, which is the variable angle toe, VAT composites, in which the fibers are no longer constant within the layer, but they can vary within the layer. This, of course, offers a and increases the tailoring capabilities, and can be helpful to further reduce the structural weight of composite structures, like the ones that I'm showing here. This is a work from Brooks and Professor Martin from U Michigan, in which they showed that by incorporating VAT, we can reduce an additional 10% the weight of the wing box. We know that composites are everywhere, and but we still lack some information on their modeling. So what I propose is to conduct a multiscale modeling of composites, because these kind of materials are heterogeneous and they are hierarchical. So this means that the innermost scales influence the outermost scales. And in addition to this, when we try to model these different scales, from a modeling perspective, we employ different structural theories. For instance, when we are modeling layers at the layer scale or a larger structure, it's a common approach to use structural theories that were originally derived for single layer structures or metallic materials. This is a drawback in modeling, because we are using simplified models that are not able to capture these continuities in the thickness direction of composites. And in addition to that, we are also employing other failure indices or invariants that may influence the safety margins and reduce the design space that we have. And apart from that, these classical theories are not effective when there are some discontinuities, geometrical discontinuities, or free edge effects in our laminates. So in order to capture well these singularities that may appear, we need a proper way of modeling. And what I propose to it is using the unified formulation. The unified formulation was introduced by Professor Carrera some 20 years ago. And basically, the unified formulation states that the field of displacements can be expressed as a summation of different expansion functions, which depend on the cross-sectional variables in the cross-sectional coordinates in the case of beam models, and on the thickness coordinate in the case of two-dimensional beam and plate shell models. What are the advantages of the unified formulation? Well, the main one is that the governing equations are written in terms of fundamental nuclei, which are invariant regardless of the selected structural theory that we are considering. And in our model, we can incorporate different cross-section or thickness expansions within the same model. Apart from this, if we want to analyze arbitrary materials or complex geometries or apply some boundary conditions, we can easily couple it with the finite element method. So in the end, what we have is that the field of displacement can be expressed as a combination of the shift functions, the expansion functions, and the generalized unknowns. As I mentioned, we can use different kinds of arbitrary expansions, but the most common ones, or the ones that I used during my PhD, were the Taylor, Lagrange, and Legendre polynomials for generating high-order beam, plate, and shell models. As an example here, we can see for 2D models, we can use a Taylor expansion, which is basically first order expansion. The field of displacement is linear within the thickness. or parabolic, and so on. Then for one-dimensional beam models, we can employ, for instance, hierarchical Legendre polynomials, which is a sort of PFM discretization. Then regarding the modeling approaches that we can use for simulating composites, we have two approaches. One is the equivalent single layer modeling, and on the other side we have the layer-wise models. What are the difference between these methods? So imagine that you have a laminated structure, as we can see here, 2 layers, for example. What the equivalent single layer proposes is that the information of the different layers is compacted within a, as its name says, an equivalent single layer. Well, in the case of layer-wise modeling, each layer is modeled independently. Now, if we want to solve our structural problem, we need to derive the governing equations. And we use the principle of virtual displacement. This one states that the virtual variation of the internal work plus the virtual variation of the inertial work has to be equal to the virtual variation of the external work. The virtual variation of the internal work is basically the strain energy of our structure, and we can expand this strain energy by using the constitutive law of the material, so the relation between stresses and strains, which in the case of variable stiffness, we can see that there's a dependency on the in-plane coordinates because the fiber is varying within the in-plane. And also the geometrical relations between strains and displacement. Then, if we plug everything together in here, we arrive to the so-called fundamental nucleus of the stiffness matrix. So K with the upper scripts ij, tau, and s. These fundamental nuclei are 3x3 matrices and are the building block of the unified formulation. And basically, if we loop through these different indices, so tau and s indices for the expansion functions, then move forward onto the I and j indices of the finite element, and then moving towards the different finite elements, we can assemble finally the stiffness matrix or the mass matrix of our structure. Regarding the variable stiffness composites, we have two main variation laws. The first one, which is the one that I will be showing you today for the most part of the results, is the linear variation, and is defined by 3 parameters. Phi, which is the fiber rotation angle, so you can appreciate it in here. So the angle between the x prime axis and the x axis. The x prime axis is where the direction in which the fiber is gonna vary. T naught is the initial angle, and T1 is the final angle. Then we have another strategy, which is the constant curvature, which is defined by just two parameters, T naught and the curvature of the path. Okay, so moving on to some numerical results about the macro scale modeling of these structures. This is a 2-layer plate subject to transverse uniform pressure, and we can appreciate that after doing the convergence of the finite element, of the number of finite elements, we can appreciate that if depending on the structural theory that we are utilizing, there's a variation in the predicted deflection. We can observe that by employing high-order equivalent single-layer models, we may obtain the same value of the deflection as the layer-wise model, which is, let's say, the highest fidelity model that we can get. However, despite providing the same result for the For the deflection, we observe some discrepancies in the prediction of the transverse shear stresses. And this is a problem that is related to equivalent single layer models. They are not capable of guaranteeing the continuity of the transverse shear stresses. Something similar is observed in here. We have a clamped shell subject to a transverse, to a uniform pressure. And in the upper line, we observe the in-plane stresses that we computed using equivalent single layer models and also layer-wise, and compared them to a solution provided by Abacus, solid models. And we observed that for the in-plane stresses, everything looks fine, more or less. However, when we are checking for the transverse stresses, we observe that the equivalent single layer models and the lowest order layer-wise model are not able to capture the characteristic parabolic trend in the transverse shear stress. Okay, so now we move on to modeling the mesoscale of composites. This can be applied for if we want to analyze the single fiber path and the matrix surrounding it, or we can apply it also to textiles. And the most common strategy that we find for modeling textiles, for instance, is that we create a very cumbersome mesh with a lot of degrees of freedom, 3D models, and this is very costly. So a solution that has come up in the last, I would say, 10 years is the use of embedded finite elements. With embedded finite elements, we will be modeling on the one side the fibers, so the textile, and on the other hand, the matrix. There's a problem with this kind of modeling approach because there's a redundant volume. So we need to get rid of it. And how can we do it from a variational principle perspective? So here I have the virtual variation of the internal work, and we observe that there is the strain energy of the host element. So we have the matrix basically, the strain energy of the fiber element, but also we need to subtract the strain energy related to this fiber volume, which is occupied by the matrix material. Then, by applying some interpolation between the displacements of the fiber constituents as in terms of the matrix one, and supposing that we are only applying the external loading on the host elements, we reach to the system of equations where we have the stiffness matrix of the host element, so the matrix, an interpolation of the stiffness matrix of the fibers, and we just need to solve this system of equations for the host constituent. Some numerical results on this. We can apply this methodology to perform a global-local analysis of our cross-ply underbinding, for instance, where we have this fiber embedded. This is modeled everything with one-dimensional finite elements, so beam elements. And we can observe that there's a good agreement in terms of the deflection with some reference value, and also for the longitudinal stresses, and a quite decent prediction of the transverse stresses, which is always the most problematic one to capture. But the potentialities of this method, I think, that are more evident in this slide. Here I'm modeling a textile, which is subject to a uniform loading, uniform tensile loading. With Abacus, we need more than 700,000 finite degrees of freedom, whereas the most refined model, in my case, uses roughly 25,000. And we obtain basically the same result in the stress components, but also on the displacements. Okay, so we talk about macroscale, mesoscale. Now we move on to the microscale, so fiber and matrix altogether. And for this part, I used of course, the unified formulation and coupled it with the mechanics of a structured genome, which is a theory introduced by Professor Weinbinju from Purdue University, and is based on the principle of minimum information loss. Basically, what it does is expressing the field of displacement, the global field of displacement, as a summation of a mean value of the displacement of the structure plus some fluctuations around it. Then, by doing some operations, we can express the potential of the heterogeneous structure as a combination of the purely elastic deformation, the thermal deformation, and the heating of the structure. Applying the variation asymptotic method, rewriting everything in terms of fundamental nuclei, etc., we can arrive to computing we can obtain the homogenized material properties of the composite structure. Not only for the elastic coefficients, so Young modulus, Poisson ratio, etc., but also for the coefficients of thermal expansions and the effective specific heat. Some results on this are shown in this slide. Some features that I would like to highlight in this are that we can model both fiber and particle reinforced composites. We perform the homogenization, so retrieving the effective properties of the composite material, and recover the local stresses at the unit cell level in one single run of the code. Normally in Abacus, from my experience, you need to conduct different and apply different boundary conditions to retrieve each of the different elastic components. While with this procedure, we just run one analysis. And another important feature is that the cross-sectional domain, for example here, this circular fiber, is modeled just with nine cross-sectional elements. But we capture perfectly the geometry of the cycle, because we are using a non-isoparametric description of the geometry. So that being said, we can observe that with this approach, we obtain the effective coefficient of thermal expansion, and it's in quite good agreement with other closed form solutions and also semi-analytical methods. And as I said, we can recover the local stress, the local stresses at the unit cell. And what we observe here is that in order to capture well these high stress gradients that appear, we need high order models. Otherwise, we won't be able to capture them accurately. Okay, we have learned how to model the different scales. Now is the time to understand what are the defects that we may encounter in AFP modeling for variable stiffness composites. I like to subdivide the defects that appear into two separate blocks. One, which is the deterministic defects, and the uncertainty defects. The deterministic defects are those that we can foresee where are they likely to appear, and we know, and we can know this information a priori because of a combination of the different machine parameters or the orientations that we want to achieve. On the other side, we have the uncertainty defects. This may occur at the mesoscale. We may find some fiber waviness, or microscale, or at the microscale. So, for example, we can have some variability of the fiber volume fraction or presence of voids, etc. Regarding the first kind of the deterministic defects, they are mainly two, which are known as gap and overlaps. Gaps are when we have between two consecutive fiber courses, there's an open space between them. So then when we put these components into the autoclave, these regions will be filled with resin. Whereas in the case of overlaps, these two fiber courses overlap each other, so they intersect, and there's a local increase in the thickness. Of course, the presence of these defects and their amount depends on the fiber path parameters, but also on some parameters more related to the FPE system, like the number of toes within the single course or the width of the toes, etc. We would like to find these kind of structures in which there are no defects, but however, we are going to find them and we are going to encounter them, unfortunately. So we need to model them. A simple, somehow, manner to incorporate them into our numerical model is by employing the defect layer method. The DLM is basically an homogenization technique used for defect modeling. And by using this DLM, we no longer need to use very refined meshes to capture well individually these defects. And the magnitude of the homogenization is dependent on the amount of defect that we find within each finite element. So, for example, in the case of gap modeling, what we do is vary the material properties depending on the gap area. And in the case of overlaps, the material properties are kept constant, but we vary locally the thickness proportionally to the overlap defect area. So in the end, when we model gaps, we end up with a multi-material, multi-layered numerical model, while in the case of overlap modeling, we end up with a stair-like thickness distribution. The other kind of defects that I wanted to talk are the uncertainty defects. And a strategy that we can use for modeling them is recurring to stochastic fields. So stochastic fields are a mathematical entity that allows us to spread a parameter in space following a certain probabilistic distribution. And to generate them, we can employ different methods. The ones that I used in my PhD were the covariance matrix decomposition, and especially the Carhunel-Loeb expansion. So in this case, we have a mean value of the defect that we want to impose, and then a fluctuation about it. And some of these coefficients are, there are some methods that we can use to get them, both analytical but also numerical. Okay, so how do we incorporate these multiscale uncertainty defects? Well, first we need to generate a random field. So imagine this flowchart for just one run. We generate different random fields and we apply them to the different layers in our model. So in that sense, it's a layer-wise model. And we start by the following. We need, of course, this procedure is performed numerically. So we need to integrate the governing equations. And for integrating, we use Gauss quadrature. So at each integration point, we will have a value of the random field. First at the fiber scale, which will give us two homogeneous value of the elastic material properties. Then we will move on to the mesoscale, where we are going to apply the waviness. So we have the initial orientation plus this perturbation, and this will go onto the fundamental nuclei of, and then assembling it to them in the whole stiffness matrix of the structure. Once we solve for the macro scale problem and we obtain the stochastic response of the mean strain deformation and the stresses at the layer scale, we can move back to the micro scale to compute the stochastic stresses at the fiber and the matrix. And this is what I did for, again, this case at the beginning of the presentation. So 2 layers subject to a uniform pressure. And after applying these 2 kinds of defects, so fiber waviness and variability of the fiber volume fraction, we observed that the fiber is the one presenting the greatest variability in the stresses. This is especially the longitudinal stress component. So it may lead to some push-out failure eventually. Okay, so the last part of the presentation is devoted to the structural optimization. But first, we need to define what is an optimization problem, at least for structural optimization. And basically, what we want to do is finding the set of design variables that minimize a certain objective function. We can think of the backline load or the mass of the structure, while fulfilling some requirements that can be written in terms of inequality, equality constraints, and be within some bounds of these design variables. And we can classify the optimization problem depending on the questions that we ask to ourselves. So how are we going to evaluate these functions? Are we going to use direct simulations, or we're going to employ surrogate models? Where are we going to search for this optimum? Are we going to perform a global search or more locally? And how are we going to search this optimum? Are we going to use gradient-based, adjoint methods, or heuristic approaches? So the framework that I propose presents these features. I chose the genetic algorithm because of its versatility and also because of its simplicity in programming, and also because it allows to solve some problems involving discontinuities. This solver can be used to solve mixed integer and also continuous optimization problems. By nature, the optimization in composites is mixed integer, because we are incorporating a a discrete number, which is the number of layers, but also we are combining it with continuous variables, which can be the fiber parameters. And in this regard, there might be some discontinuous responses that we need to account for them, and it's not convenient to make them continuous. Then also this framework can work for single objective and multi-objective problems, and can handle both direct simulations and surrogate models. And it works as follows. So as I mentioned, we are using genetic algorithm. So there's an initial set of a generation. Each of them have a number of plies and fiber orientations. With this information, we can evaluate manufacturing constraints, and we will keep them for later for the optimizer. So if we move back here with this info, we enter the defect quantification framework. In this, we are gonna create the input files needed to run our simulations. But also in this defect quantification framework, we can select the manufacturing strategy that we want to use, whether it's defect-free or we are going to consider gaps and overlaps within our models. So after we create the inputs, we fed them to the curve-based finite element code, which will give us the quantity that we want to optimize. Then with this information, the constraints and the value of the objective function, the genetic algorithm will perform its operations, and we will check for convergence. If we found a design which is quite similar to previous ones, okay, we are done. Otherwise, we restart for the next generation. Okay, so now I will show you some results on the structural optimization. These are the only results in the presentation that are not mine. They are from my colleague Avin from University of Washington. And what he tried to do is minimizing the stress concentration factor around a hole, which can be representative of the window of an aircraft. And he decided to use a quite different modeling approach for BAT. Instead of using the T0, T1 formulation, he used some Bezier curves. He incorporated already the manufacturing signature of the machine, and he employed the abacus to solve the structural problem. It was a single objective optimization, used continuous variables, and instead of performing each simulation, he trained a neural network to solve the problem. And in the end, what he found was a combination of a layer in which there were some overlaps for the first layer, let's say, and in the second layer there were some gaps, as we can observe here. And in the end, the new solution provided a stress concentration factor, so here at this point, equal to 3.8, which represents a 32% reduction compared to this quasi-isotropic design. This quasi-isotropic design had a stress concentration factor equal to 5.6. So there's a great advantage of using this kind of technology. The second set of results corresponds to the backend optimization of a variable stiffness plate. In this case, I incorporated also some manufacturability constraints. And what I wanted to investigate was the effect of the selected structural theory. What is the effect of the structural theory on the retrieval of the optimal design variables. And we can observe that more or less we get similar trends in the fiber paths for both the thick and thin plates. In the case of thin plates, the predicted value of the backing load there are no such big differences, because in the end the shear stresses that do not play such a high role, and we can neglect them. But when we move to thicker plates, the structural theory influences a lot the predicted value of the magnitude of interest. Okay, so now the last set of results concerns the least weight optimization of a composite structure subject to a compressive load. In this case, we wanted to find the minimum number of layers and finding the fiber orientations that guarantee that the backline load will be greater than a fixed reference value. At the beginning, we tried to use a single optimization, a single objective optimizer, but as I mentioned earlier, because of the nature in composites optimization, is that it's a mixed integer problem that we have to solve, and single objective optimizers do not perform well. So we decided to employ a multi-objective strategy. In this case, we will be minimizing the mass and maximizing the buckling load. As design variables, we are using the fiber orientations, which are continuous variables, and discrete variables, which is basically the number of layers that we consider. And last, we also consider the manufacturability constraint, but we aggregate it into just one single metric in order to speed up the optimization process. In the case of multi-objective optimization, we do not find a unique solution, but we find multiple solutions, which in this multiple non-dominated solutions, which are known as the Pareto front. And yeah, so basically by using this multi-objective strategy and applying it for this problem, we first decided to consider the defect-free plate. And what we observe in these plots and in this table is that there's the first thing that comes to our mind is the evidence of the discrete nature on the optimization of composites, right? So we can see that for each number of layers, there is an optimum solution that we can find. The second thing is that the different Pareto fronts are quite similar between each other, regardless of the structural theory that we apply for the defect-free configuration, as we can observe here in these plots, but also on the tables. Now, if we want to incorporate the manufacturing signature, we can do it first for the full gap strategy, and again, in these plots, we observe the discreteness of the structural optimization in composites. In this case, the differences in the mass are related to the gap modeling, because in the end, as I mentioned earlier, when we have gaps, there are resin-rich areas. So these modify the density of our structure, and therefore the final mass. The second thing that we observe is, okay, more or less we can find the same Pareto fronts for the different structural theories, but if we look carefully, there are some discrepancies, and these are observed especially for the constraint case, where we have different fiber paths and also different trends in the fiber paths compared to the other structural models. In this case, the equivalent single layer of first order it's a model we can find on Nastran or Abacus. It's basically a Reisman-Middling theory. And as I said some slides ago, when we are modeling gaps, we are basically building a multi-material, multi-layer structure. But what are the problems of classical theories like this one? That they are not able to account for the discontinuity in the thickness direction. So they are not going to provide us a good optimal solution like other high-order structural models do. The last numerical case incorporated the overlaps into the design. And here, the discreteness of the process is not so evident because the material properties are constant, are kept constant, do not vary. But as I mentioned, we modify locally the thickness of the finite element. And what we observe here is, again, at least for this case, in the complete overlap, weak influence of the structural theory, both for the, as we can appreciate in both Pareto fronts, but also in the table. And this makes sense because, at least for the plates that we were considering, they are quite thin. So the shear components are not so relevant, and and in these models we don't have the discontinuities in the material properties as in the gap case. These are the different optimal solutions of the constrained optimizations, and we can observe that the optimal solutions are completely different. So the fiber paths, depending on the manufacturing strategy that we are considering, are completely different. So this means that we need to consider them into the optimization process. So just to finish today, I would like to mention that, well, I have presented my work, my PhD work, and it corresponds to a high fidelity multiscale and multimodal framework in which we can incorporate fabrication flows. We can generate high order beam plate shell models that can correctly predict the stress state without needing cumbersome and expensive 3D models. We have also seen that we need layer-wise models to capture the variability in the stress state that appear because of the manufacturing defects. And more related to the optimization part, we have seen that BAT can improve the performance compared to straight fibers, and even reduce the structural weight of the structure. So, for example, here with the complete overlap, we are able to save up to a 35% mass compared to the other optimal solution, to the reference optimal solution. And as I just said, we need to incorporate the manufacturing signature of the manufacturing process into the optimization, because we can see that there are different optimal solutions depending on the strategy. As future perspectives, well, I would like to continue to develop the embedded models for mesoscale and microscale progressive failure analysis. Now the challenge that I find is whether choosing discrete modeling or continuum damage models. I would like also to investigate reliability-based design optimization for BET. But the challenge here is that for computing some of the probabilistic responses, we need layer-wise models, and they are way more expensive than equivalent single layer models. So a possible solution to it would be incorporating multi-fidelity models and machine learning. And last, I would like to continue research on AFP systems and try to find what is the relation between the machine parameters that we select and the defects that we are going to encounter. So this will allow us to develop digital twins that can help us to improve the fabrication processes and modify on the fly, for instance, the parts that we are manufacturing. And this is always in the framework of the famous Industry 4.0. But here the challenge is getting an AFP system. So I think there's room for collaboration with my colleagues in University of Washington. I also want to thank the ERC, the Preeco project of my advisor Alfonso Pagani, and also the support of Embraer. So that's it for today. If you have any questions, I'm here to try to answer them.
Okay, so thank you, Alberto, for the talk. Now we have time for questions.
Hi, Alberto. Thank you very much for the very compelling presentation. I have a question on the optimization framework. In the sense of what is the, for example, yes, the last examples, what is the scale of the problem in terms of nodes, in terms of total, for example, the initial population you mentioned of the GA and so
on? So we built this framework on a commercial software called Mode Frontier, where you can select the initial samples. Right now, I don't remember well how was the initial design of experiments, but considering, for instance, that we have up to six layers. But well, in this case, we were considering symmetric lamination. So in the end, we have the number of design variables. So I would say, so it would be 6, 7, around. And also because of the nature of this kind of problem, maybe the initial design of experiments would be around 100, more or less, of individuals. But that's a parameter that you can tune on the optimizer, or even the optimizer can maybe, if he sees that with 50 samples is not sufficient, he increases it automatically. So yeah, it depends maybe on the problem, but I would say around 100 maybe.
Thank you very much.
Thank you.
Okay. Thank you, Alberto. Thank you very much for the presentation. Just one question related to the multiscale. So if you go to the microscale model, where you model actually the fiber and the matrix with all the interaction, do you use that to calculate the mesoscale stiffness and strength, right?
Yeah, I mean, actually with this you calculate the homogenized properties of the whole composite material.
Exactly. So here, you know that if you change reference frame and you're considering core fiber, the stress distribution, therefore the stiffness and the strength would be different. Why did you use a straight, let's say, microscale model to model the strength of a curved one?
Okay, so yeah, this framework foresees that there's a let's say a scaling factor between them, and there's the repetitiveness of this. So yeah, initially we consider straight fibers, but then yeah, it made us think, okay, but we are talking about variable stiffness, so maybe we need to incorporate curved fibers. So that was actually the motivation for deriving the embedded models. So this could be interesting to expand, let's say, the microscale formulation and expand it to embedded finite elements to perform homogenization in curved fibers. So yeah.
Because let's say, as it's developed now, it's okay with a certain kind of curvature or curvature radii, because then if you go for serious curvature around, for instance, a notch or something like that, then you need to use a polar or a cylindrical coordinates where the strength is slightly different. Okay, thank you. And if I may ask something else, related to, let's say, to the manufacturer-induced defects that you can have steering the toe, right, with the AFP, because AFP generally use toe that are designed for straight lamination. When you curved, you got difference in terms of, let's say, the equivalent of the crushing load, so the displacement when you curve, so the fiber change their density, basically. Do you consider that just with this kind of model with the gap, or do you even consider at the microscale model the variation of the, because your elements, your reference volume would change, for instance, in this case?
Okay. No, so with the kind of modeling that we used, it was just, let's say, at the mesoscale. So we didn't consider the microscale. But I think there are some, I've read of some models that incorporate the microscale in it's something like IDLM or something like that. But yeah, it is incorporated also the microscale. So yeah, it will be interesting to use it as well in this framework.
Thank you. Thank you very much.
Thank you.
Thank you, Andrea. So is there any more questions?
I have a curiosity. The machine for layering the composites. How much would it cost?
I think I was talking about this the other day with Andrea, and he said around 350K minimum, right? Or the AFP machine, like.
Yes. Depends on the different AFP.
Yeah.
Sorry, I was confused by the composite. No, yes, can be around. Let's say the cheapest one, probably used, we can even do 200K. But a good one that allows us to do research for more than 10 years, 350, 400K.
Yeah, so I don't know about the cost. I know more or less the facilities that the University of Washington has, and they have like the ultra fancy AFP, and they make you pay a lot if you want to use them. So I think that price would be quite expensive. It's an electro impact machine, by the way, but yeah, there might be some more affordable AFP systems.
Thank you.
Okay, so I think it's time to close the session. So let's thank the speaker again.